Okay, hi everyone, welcome back. In this video, we are going to be working through the entropy of reactions. So in the last video, we really set out Hess's law and enthalpies, and now we're going to try to think about how the second law of thermodynamics applies and works with us for reactions. Okay, so in this, we're really going to start thinking about the spontaneity of reactions. And with this, we're going to see that the second law of thermodynamics still applies. And so the second law of thermodynamics says that if the change in the total entropy is positive, then things will be spontaneous. This applies to reactions as well. So a reaction will be spontaneous. In other words, no work will be required if the reaction maximizes the total entropy of the universe. And this is the second law of thermodynamics. Now, just like before, when we talked about heat transfer, where we said that Q equals TdS, this must be a reversible process. And it turns out that we're going to get there, but it turns out that reversibility is much easier to achieve in reactions than it is in expansions and contractions. And so since Q reversible equals TdS, we know that delta S of the surroundings is going to be equal to negative delta H of the system divided by T. And this is for a constant temperature sort of situation. At constant temperature, we have our Gibbs free energy. And we're not going to do a lot about that in this video. But the next video, we're going to move into Gibbs. At equilibrium, this delta G of the reaction will be equal to 0. And what this does is these principles for spontaneity of reactions bring together three key concepts: the entropy of the reaction through the second law, the reversibility of the reaction, and the free energy. And in the videos that we're working on, we're going to work through these ideas. And today, in this video, we're going to talk about the entropy of the reaction. So, to do this, let's go back to Boltzmann. This is where we started the semester, and it's where we keep returning to in order to understand spontaneity. So, for spontaneous reactions, the total entropy will increase. This is the second law of thermodynamics. The Boltzmann definition of entropy is still true, where the entropy is equal to K log omega, and omega is defined as our number of microstates. So if the amount of disorder is increasing, if the number of microstates is increasing, then things will be spontaneous. So let's talk degrees of freedom and trying to very qualitatively predict if something is going to increase or decrease its entropy. So if we consider the reaction of two water decomposing to form H2 gas and two OH gases, and we wanted to think about what is happening to the entropy, we would need to look at the entropy of the products and the entropy of the reactants and consider the difference between those. And so to do this, we really start thinking about these degrees of freedom, and this is really working into this idea of NEP, that equipartition that we talked about at the beginning of the semester. So with the reactants, in this case, we have two molecules of water. Each molecule of water has 3 translational degrees of freedom, 3 rotational degrees of freedom, and 3 vibrational degrees of freedom. Remember, nonlinear becomes 3n minus 6. And so if I add those together and multiply by 2, because I have 2 molecules, I find that there are 18 degrees of freedom for the reactants. And I can do the same thing for the products, but notice I have 2 different types of products. So each OH molecule has 3 translational, 2 rotational, and 1 vibrational degree of freedom, giving me 12 degrees of freedom from my OH. My H2 has 3 translational, 2 rotational, and 1 vibrational, giving me 6. The total degrees of freedom, and this is in the wrong spot, but that's okay. The total degrees of freedom is going to be equal to 12. Oh, it's not in the wrong spot. 12 degrees of freedom from the OH molecules and 6 from the H2, giving me 18 degrees of freedom for my products. Now, notice that there is no difference here, that I have conserved the degrees of freedom. So equipartition is not by itself is not going to give us a good view on whether or not we're going to increase or decrease the entropy during the course of this reaction. So now we really have to think, but what we have to do is we're going to have to think much more closely about these translational degrees of freedom. And so if we think about a box that is filled with H2O, and we think about a box, so this one just has water. And then we think about another box under the same conditions. And this box, it has H2 and it has OH in it. And the question becomes, which of these, how does the entropy compare between these two conditions? And it turns out that we know that whenever we mix things, the entropy goes up. And so because we have 2 molecules in this box, that the entropy, the number of microstates of the products, is going to be greater than the number of microstates of the reactants. And this really comes from this mixing and this translational degrees of freedom. So the kind of take-home message of this is that the more moles of gas that we have, the more translational degrees of freedom there are, and thus more entropy. So we can kind of eyeball a reaction. And if we are creating more gas, we can assume that the products have more entropy. Thus, we would start leaning to expecting this reaction to be spontaneous because entropy is increasing. Now remember that spontaneity is based on the total entropy. And so when the system is increasing entropy, it's a good indication that things will be spontaneous, but not a guarantee. To guarantee spontaneity, you're going to have to understand both the system and the surroundings. Okay, so now let's think about this a little more closely. If we have the reaction H2 plus Cl goes to form HCl plus H, and we started to think about this as, do the products or the reactants have more entropy? Well, as we think about this, my reactants have 2 moles of gas. My products, they have 2 moles of gas. And so it's very difficult to be able to predict which of these is going to have more entropy. The degrees, at this point, the degrees of freedom are identical for the products and the reactants. And so we're going to have to figure out how to calculate this delta S of reaction instead. And so to do this, it turns out that we are going to basically use Hess's law. And these standard molar entropies, so these are standard molar entropies, these are tabulated in the appendix of your book. And so if we take the V, this is the moles, times the standard molar entropy from the table of the products minus the reactants, we can calculate the delta S of the reaction. This is exactly like what you did in the enthalpy problem in the last video. And so what we do is I looked up these numbers from the table and rounded them to a reasonable number of sig figs. And if I calculate things out, you find that this delta S of reaction is a positive 7 joules per Kelvin mole. So this is small. It tells us that we expect this to be spontaneous based upon the system, and that the products have more entropy than the reactants because of this positive number. So entropy is increasing. Where does that come from? It comes from the vibrational and rotational structure of HCl versus H2. This is when we started talking about if things have heavier atoms, that they are more likely to have lower lying rotational and vibrational states, and thus having more of that vibrational and rotational contributions. And this HCl is heavier and has more vibrational and rotational contributions to these degrees of freedom than the H2 does. But on the surface, predicting that is really tough, and so what we like to do is calculate it instead.